Today we're going to look at the mean value theorem and Rolle's theorem. The Rolle's theorem is just a small subset of the mean value theorem, yet a little different. So we usually study these together, and we'll start with Rolle's theorem. So it says, suppose that y equals f of x is continuous at every point of the closed interval a to b, and differentiable at every point of its interior a to b. So those two statements, that's a condition for a lot of these things. If f of x is continuous and differentiable, and f of a equals f of b, then there is at least one point c in a to b at which f prime of c equals 0. So like most of the theorems, they're written in a very technical way. So we have to decode what that says and find a statement that makes sense to each of us to understand this. So this first prompt says, in your own words, explain Rolle's theorem. And the way that I would do that is something like this. So I'd probably write this more technically than you might, but whatever you come up with to remember it is fine. So it says, on an interval a to b, if a function has two of the same y values, and I'm getting that from this third step, then the derivative will be equal to 0 at some x value in the interval. So you'll see I just restated Rolle's theorem. I did leave out the continuous and differentiable part, usually because I don't have to think too much about that in terms of the type of questions that I'm asked about this. And what I'll do with this, I'll show you a picture that I drew. So right next to it, I sketched some function f. And in my translation of the theorem, so it says if a function has two of the same y values. So you can see that f of a is at 3 and f of b is at 3. So f of a equals f of b. And so if that happens, then it says the derivative will be equal to 0 at some x value in the interval. So what this is saying is that if you have two y values like f of a and f of b, in order for the function to go from f of a to f of b, it has to have some kind of dip or peak or something like that, which means that it has a 0 derivative. So to go from f of a here, you have to go down, and then you go back up, and then as soon as I go back up, I have this dip, which would be where the derivative is equal to 0. So it's a really simple theorem. It's common sense in a lot of ways, and pretty easy to apply for this one. So next we have the mean value theorem. So the mean value theorem states that if y equals f of x is continuous at every point of the closed interval a to b, and differentiable at every point of its interior from a to b, which are the two same conditions that are listed for Rolle's theorem, then there is at least one point c in a to b where f prime of c equals f of b minus f of a divided by b minus a. And I'll just highlight that part because that's going to be the form that we're going to use the most. So let's just kind of restate this thing. So if a function is continuous and differentiable on a closed interval, then the derivative, f prime of c, is going to be equal to the average rate of change. So f of b minus f of a divided by b minus a is the average rate of change. So the average rate of change is just the slope of the secant line between 2 points, and the derivative is the slope of the tangent line through 1 point. So we're saying that if you have those conditions, there's at least one place where this is going to happen. So if I restate that in writing, I wrote that here. On an interval a to b, a function's average rate of change from a to b will be equal to the derivative at some point c on the interval. So the visual for that is right here. So I'm going to draw that green arrow again. But so in purple, you have the average rate of change. So that's the dashed purple line. And in blue, we have the derivative, so the dashed blue line. So if you have a secant line between those 2 points, the slope of that secant line is going to be the same as the slope of the tangent line at some point between those two values. So I'll demonstrate the mean value theorem using Desmos because it's much better to look at a moving image versus a static image on a page. We have the secant line in blue, some function. The function is continuous between those 2 points, so it meets the conditions. It's differentiable. And what the mean value theorem says is that the slope of the tangent line is going to be the same slope as the secant line at some point between the 2 blue points on this graph. So if I turn the tangent line on, you'll see there's the tangent line, and I can move this thing around so it can, it's showing me all of the slopes between those 2 points. And what the mean value theorem says is that at some point these are going to match if the function's continuous. And there it is. So it turns green when it matches. So that now has the same slope as the blue line. And that is what the mean value theorem states. Okay, so let's do a couple examples. First question, find a point C that will satisfy the conclusion of the MVT for the function y equals root x on the interval 9 to 25. In other words, for what value of x on the function has a tangent line with the same slope as the secant line passing through the graph at x equals 9 and x equals 25. So we need to take the derivative and then we need to set it equal to the average rate of change. So let's take the derivative here. So y prime. Well, y is root x, so y prime will be 1/2 x to the negative 1/2. And I will simplify this because I'm going to have to use it in a different form. So that's 1/2 root x. Okay, now the average rate of change. So the average rate of change between those two is f of b minus f of a divided by b minus a. So f of b, if I use 25, would be root 25 minus f of a, which is root 9, over 25 minus 9. Okay, so in the numerator I get 5 minus 3 over 16. 2/16, 1/8. So then we're looking for a point C that will satisfy this. So all I have to do is take the derivative and set it equal to the average rate of change. So I will change that to a C in this case. So this is 1/2 root C equals 1/8. And we just solve this, and that C value will be our value. So this would be 8 equals 2 root C. Divide by 2 and you get 4 equals root C. And then we just square this. So C equals 16. Okay, so the next question is more of a general question, but it's an important one. What can you conclude about the function if f prime of x is positive? What if f prime of x is negative? Well, this is a pretty simple thing here. So if f prime of x is positive, what's the function doing? F is increasing. If f prime of x is positive. So if f prime of x is negative, well, f is decreasing. All right, so the next one, describe when a function is monotonic. So this just is more vocabulary that you need to know in order to solve problems. A function is monotonic if it is strictly increasing or decreasing on its entire interval. So this is when f is either increasing or decreasing on its interval. All right, so the last big idea in this section is the first derivative test. So the question is, what does the first derivative test determine about the function and how does it work? Well, the first derivative test determines relative mins and maximums. So I'll write this in 3 different sentences. So if f prime switches from negative to positive on either side of C, f of C is a relative minimum. So that means if the slope changes from negative to positive, then that means C would be a minimum. All right, so we'll do an example that kind of helps you visualize this. And what I'm going to do is just actually duplicate this because the next part is pretty much the same with just a slight change. So number 2, if f prime switches from positive to negative on either side of C, then f of C is a relative maximum. Okay, so we're talking it's a maximum if it goes from positive to negative, and it's a minimum if it switches from negative to positive. I think I said that right. And then if neither of those things happen, then that point C is not a minimum, nor is it a maximum. So the last thing is, if neither happens, then f of C is neither a min nor max. Okay, so let's just put this into practice. So for the number 8, and this is the entire first derivative test. It says from the chart below, what can be concluded about the function if the x values are critical points? Okay, so we have this sine chart, and it says sine of f prime of x. That's hard to read there. And it goes from positive to negative, and then negative, negative, positive, or negative, positive, positive, negative. So, well, let's look at each of those points. So where does it switch? It switches at -5, it switches at 5, and it switches at 10. So at 0, you have negatives on both sides, so that means that it doesn't, there's not a min or max there, so we won't even look at that one. So the first thing is that x equals -5. It went from positive to negative, so that's going to have this, goes positive slope, then negative slope. So that is a relative max. Okay, for the second point, x equals 5. Well, that one does the opposite. It goes from negative slopes to positive slopes. So x equals 5 is a relative minimum. And the last one, it goes from positive to negative, so that is a max. So x equals 10 is a relative max. So the first derivative test is very basic like that. Okay, so here's a full example of the first derivative test. It says find the critical points in the intervals where the function is increasing and decreasing. Then use the first derivative test to determine whether the critical points are a local maximum, minimum, or neither. So to find the critical points, we're going to take the derivative and set it to 0. So f prime of x is 3x squared minus 24x. And then we set this to 0. So your critical points are x equals 0 and x equals 8. Okay, so to find the intervals of increase and decrease, we draw a number line, put our critical points on that number line, and then we just test values in the derivative to see if the slope changes from positive to negative or negative to positive. So let's first look at numbers below 0. So we have to check in each of these intervals. So I'll choose -1. It's f prime of -1, so I'm plugging it into the derivative. And if I do that, I would get a positive number out. I don't care what the number is, I just care about the sign. So this is a positive on the number chart. We plug in a number between 0 and 8. I'll choose 1. And again, we're plugging into the derivative. So I plug in 1 here, for both 3x squared minus 24x, and I would get a negative number. Then we check something above 8. So I'll choose, doesn't matter how big or small, so let's choose 10. You can use, so we're using the derivative, so we plug it in there and we would get a positive number. So f prime of 10 would be positive. Okay, so that is how we generate the number chart. So where is it increasing? Well, it's increasing where the derivative is positive. So the interval -infinity to 0, that is an increase, an interval of increase. And then from 8 to infinity is also an interval of increase. So where is it decreasing? It's decreasing when it's negative, so from 0 to 8. So local maximums and minimums. It's going to be a maximum if it's a positive slope than a negative slope. So on the sign chart, that happens at x equals 0. And then you can see that at 8, you have a slope change from negative to positive. So that is a local minimum. And there's a question down there that says neither max nor min. This doesn't apply because both of the critical points were one or the other. So that's one full application of the first derivative test.